Hello and welcome. In this video, we're going to learn about inductive and deductive reasoning. Our objectives are that I can use inductive reasoning to make a conjecture based on pattern, that I can use deductive reasoning to create a logical argument. We're also going to talk about the law of detachment and syllogism, which will allow us to use deductive reasoning. So let's go ahead and jump in. As usual, we're going to start with vocabulary. Our first vocabulary word is conjecture. A conjecture is an unproven statement based on observations. This happens a lot in science classes where we run an experiment and we make a conjecture based on that. Inductive reasoning is when we find a pattern and create a conjecture based on that pattern. My math teacher gave me homework yesterday, so my math teacher will likely give me homework today. So we're creating a conjecture based on a pattern that we have observed. I'm actually going to jump down. Deductive reasoning is when we use facts, definitions, properties, different laws of reason to create a pattern. This is the one that we're going to use the most often in math. And specifically in this class, when we're creating a proof, we're going to be using those definitions, properties, and facts. Last vocabulary word before we get into a couple of laws down below is a counterexample. A counterexample is just an example that disproves a conjecture. So we were talking about inductive reasoning, and I gave the example that my math teacher gave me homework yesterday, so I'm going to have homework today. Any day where we didn't have it homework would be a counterexample to that claim that was based on inductive reasoning. So a counterexample is just, here's an example that disproves this statement. The laws of detachment and the law of syllogism are just something that we use when we're reasoning to create deductive reasoning. So this isn't something I necessarily care about you knowing by name, but it is something that we will be using one way or another. The law of detachment says if the hypothesis of a true conditional statement is true, then the conditional statement is true. So if we know something is true, then we can conclude something else. You'll see examples about those towards the end of our notes today. And then the law of syllogism really just says, I almost think about it like the transitive property. If we know a hypothesis leads us to a conclusion, and we know that conclusion leads us to a second conclusion, we can sort of cut out the middleman and say the original hypothesis will lead us to the second conclusion. So there's sort of an overlap in true statements that allows us to conclude a third statement. So right now, these laws aren't going to make sense so abstractly. I promise we're going to get to some examples where you're going to see them in action. So let's get into some examples in general so that we can really make sure we understand these vocabulary words. All right, on our first examples, we're just going to focus on pattern recognition. So we're going to sketch the next figure that would exist in the pattern if we continued in the way it's currently going. I encourage you to pause the video and go ahead and draw the next figure and then unpause the video and see how you did. All right, hopefully you have had time to work through this. On number 1, I notice originally the circle has 2 equal parts, and then it has 4 equal parts, and then it has 6 equal parts. So I need to draw a circle that now has 8 equal parts, and it looks like I'm just shading one part. So here's what my next figure is going to look like. Now, number 2, I hope that the coloration here is showing up well, and I apologize if it is not. Each figure is a star, and originally there's just one piece that's not shaded, and then there's 2 pieces that aren't shaded, and then there's 3 pieces that aren't shaded. So likely the next piece would be a star that has 4 pieces, so this piece wouldn't be shaded, or it only has 2 pieces shaded. So that would look something like this. And then lastly, we have 1 circle, we have 3 circles, or I'm looking at the base. The base is 1, the base is 2, the base is 3. So I'm going to draw a pyramid that has a base of 4 that also goes up 4. And there is what my next figure would look like. It's also important for us to be able to say out loud or express in words what these patterns are, so make sure that you can do that as well. Let's look at a different kind of example. Now we're going to move on to making conjectures. So we're going to look at a situation, we're going to look at some sample cases, and then we're going to draw a conjecture or draw a conclusion. It may be true or it may be false based on the sample that we're looking at. So number 4 says numbers such as 3, 4, and 5 are called consecutive integers. Make and test a conjecture about the sum of any 3 consecutive integers. So let's start with the one that we were given. If we add 3, 4, and 5 together, we get 12. If we add 4, 5, and 6, I'm just going to look at another case. If we add 4, 5, and 6 together, we get 15. If we get, let's go totally different, 10, 11, and 12 together, we get 10 plus 11 plus 12, we get 33. If I add, let's say, 100 plus 101 plus 102 together, I'm going to get 303. And then we're supposed to come up with a conjecture just based on what we're noticing. So something that I noticed, especially with these 3 numbers, but it's also true of this one, is that all of these numbers happen to be divisible by 3. So my conjecture may be true, may be false. I haven't proven it, but my conjecture, based on my observation, is that the sum of 3 consecutive integers is a number that is divisible by 3. Why don't you go ahead and pause the video and try to come up with a conjecture for number 5 about the product of any 3 negative integers, and then unpause the video and see how you did. So hopefully you've had time to look at that. I just listed out 3 cases here, and I'm trying to look for a pattern as I write my conjecture. And this one you may have already known, but it seems like if I multiply 3 negative numbers together, I'm going to get a value that is negative. So that's what I'm going to write as my conjecture. And there we go. So we are coming up with a statement that we believe to be true based on the cases that we looked at. Now, sometimes we are looking at conjectures that are not true. And in that case, we can disprove those using another one of the vocabulary words in this lesson, which is a counterexample. So for each of these 3 problems, they give a statement that is not true, and we're going to come up with a counterexample to disprove that statement. So let's look at number 6 together, and then let's see if you can figure out 7 and 8 on your own. Okay, number 6 says the sum of 2 numbers is always more than the greater number. So they're saying if I add 2 and 3 together, I get a number that's bigger than the greater number. So in this case, that actually does hold true. So this is not a good counterexample, but that's the statement that they're saying. If I add 2 numbers together, their sum is going to be larger than the greater number. So when I'm trying to think of a counterexample here, I'm thinking about something like, well, what happens if I add 0? In this case, 3 is not greater than 3. It's the same, so this is a counterexample. Another counterexample would be if I added a negative number. If I add a negative number to a positive number, it's going to decrease, and this is definitely not bigger than the larger number. So we only need to come up with one. So a counterexample here on number 6 would be the numbers 0 and 3. And again, we can see right here that when I add them, their sum is not greater than the bigger number. So I'm going to encourage you to pause the video and try and come up with a counterexample for numbers 7 and 8. And then unpause the video and see how you did. All right, hopefully you had time to look at these. Number 7 says the value of x squared is always greater than the value of x. My first thought is what happens if I square 0? I get 0, and 0 is not greater than 0. So a counterexample on number 7 would be 0, since 0 squared is not less than 0. Another counterexample, again, we don't have to list more than one, but if I square a fraction, that fraction actually gets smaller as long as the value of the fraction is somewhere between 0 and 1. But we just need one counterexample, and 0 is a great counterexample here. Number 8 says the sum of 2 numbers is always greater than their difference. So if I subtract 5 and 3, I get 2. If I add 5 and 3, I get 8. So this holds true for this statement. So again, my next thought is either I could use 0 in some way and see if that's true, or I could use negative numbers. Since I already used 0 on 2 examples here, I'm going to try something different. I'm going to try negative numbers. So if I add, so let's say our numbers are -2 and -1. If I add them, I get -3. If I subtract them, I get -1. And -1 is actually larger, so a counterexample in this case could be -1 and -2. And there we have it. So a counterexample is just something that disproves a claim. All right, for our last few examples, we are going to be looking at different problems and seeing if we can draw conclusions using the laws of reason that we mentioned in the vocabulary section here. I'm not overly concerned that you know the names law of detachment and law of syllogism. I really just care that you can draw the conclusions based on the statements that are given. So let's read through each of these problems and see where we can go. Number 9 says, if two segments have the same length, then they are congruent. We know that BC equals XY, which means we know that they have the same length. These two segments have the same length. Using the law of detachment, what statement can you make? So if we know two segments that have the same length are congruent, and then we know these two segments have the same length, what we can conclude is that these two segments are congruent. And the symbol that we use for congruent is the little equal sign with the squiggle above it. So that's the conclusion that we can draw using the law of detachment on number 9. On number 10, it says, what conclusion can you make about the product of an even number and any other integer? So if we have an even number like 2 and I multiply it by any other integer, 5, 2 times 3, 2 times 2, I'm noticing that no matter what happens, if I multiply 2 by any other number, or if I multiply an even number by any other number, I'm going to get an even number. So this is just trying to get us to be able to draw a conclusion based on fact. And that makes sense because the definition of an even number is that it's a number that can be evenly divisible by 2. So 2 times some value, and all we're doing here is multiplying by 2. If we multiply by another even number, let's say we multiplied some number by 4, well, that's really still the same thing as 2 times some number. So you don't necessarily have to follow this logic here, but the statement that we can conclude is that the product of an even integer and any other integer is going to be even. Okay, number 11, if possible, use the law of syllogism to write a new conditional statement that follows from the pair of true statements. So if x squared is greater than 25, then x squared is greater than 20. If x is greater than 5, then x squared is greater than 25. So we're sort of just trying to read between the lines here. I noticed that we have this repeated statement. So what we can do is we could rewrite the other statements. If x is greater than 5, then x squared is greater than 20. So we're sort of just cutting out the overlap. Since the hypothesis of one statement is the conclusion of the other statement, the law of syllogism applies here. For part B, if a polygon is regular, then all the angles in the interior of the polygon are congruent. If a polygon is regular, then all of its sides are congruent. So in this case, we don't have that overlapping statement, so we can't draw a conclusion based on the law of syllogism here. So we're just going to say nothing can be concluded with this law based on the way that this statement is written. Okay, we're going to look at one last example to make sure we understand the difference between inductive and deductive reasoning, and then we will wrap up this video. All right, here's our last example. We're going to decide if inductive reasoning, which is reasoning based on a pattern, if inductive reasoning is being used, or if deductive reasoning is being used, which is this is going to be some logic or rule that is allowing us to conclude something. And then we're going to explain our reasoning. Each time Monica kicks a ball up in the air, it returns to the ground. So the next time, these are keywords that make me guide towards inductive. So the next time Monica kicks a ball up in the air, it will return to the ground. So this is inductive reasoning because our conclusion is based on an observation of a pattern that has happened repeatedly over and over again. So we're going to say this is inductive reasoning since it's based on a pattern. If this same problem said every time Monica kicks the ball into the air, it returns because of gravity, so when she kicks it, it will return because of gravity, then we're applying logic and the law of gravity, which would mean it could be deductive reasoning. But in this particular case, the way this problem is written, we are identifying a pattern and using that to draw conclusions, so that is inductive reasoning. Number 12, part B, says all reptiles are cold-blooded. So this is a definition here. All reptiles are cold-blooded. Parrots are not cold-blooded. Sue's a parrot, so she's not a reptile. So in this case, we're using a definition of reptile, which means cold-blooded, and then we're using that to draw a conclusion. So this is deductive reasoning because it's based on facts and definitions or laws of logic. And there we have it. So that's the difference between inductive and deductive reasoning. Let's go ahead and wrap up this video. All right, 2.2. In this lesson, we looked at inductive reasoning and made conjectures based on patterns. We looked at deductive reasoning, where we created logical arguments based on rules, definitions, specifically focusing on the law of detachment and the law of syllogism. And we found counterexamples to disprove claims. Lots going on in this lesson, but go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.